Einen schönen guten Abend, liebe Kolleginnen, liebe Kollegen, liebe Gäste. Als Studiendekan begrüße ich Sie ganz, ganz herzlich zur heutigen Antrittsvorlesung vom Kollegen Professor Slabon aus der anorganischen Chemie. So eine Antrittsvorlesung, und ich habe mir vorher mal den Lexikoneintrag, was eine Antrittsvorlesung genau ist oder wie sie definiert wird, angeschaut. Und dort ist zu lesen, dass eine Antrittsvorlesung ein festlicher akademischer Akt zu Beginn der Lehrtätigkeit eines neu berufenen Professors ist. Festlicher Akt kann man auf jeden Fall sagen, stimmt. So viele von Ihnen sind hier erschienen, da freuen wir uns sehr. Zu Beginn einer neu berufenen Professur ist vielleicht nicht so ganz richtig. Adam ist schon eine ganze Zeit hier bei uns im Haus, aber aus allen möglichen Gründen findet die Antrittsvorlesung erst heute statt. Tatsächlich sind solche Antrittsvorlesungen schon sehr, sehr alte Universitätstraditionen. Ich habe auch herausgefunden, dass es im deutschsprachigen Raum das schon seit 1500 an einigen Universitäten diese Tradition gibt. Damals war es üblich, die Antrittsvorlesung auf Latein zu halten. Das bleibt hier heute erspart. Einige von Ihnen werden sich vielleicht noch an den 30. November 2006 erinnern. Du, Peter, Sie, Herr Altenbach. Das war nämlich der Tag, wo ich hier gestanden habe für meine Antrittsvorlesung. Und für mich war das was sehr Besonderes, ein schönes Gefühl, im Kreise der Professorenschaft hier in der Fakultät aufgenommen zu werden. Und ich hoffe, dass du nach der Vorlesung mit demselben Gefühl hier wirklich angekommen bist. Das soll von mir genug sein. Ich möchte aber kurz noch Professor Slabon vorstellen. Er hat einen sehr bewegten und internationalen Lebenslauf, gebürtig in Polen, in Deutschland zur Schule gegangen, in Nürnberg studiert, in der Schweiz promoviert, zu einem Postdoc in die USA, zwischendrin noch ein Master in Polen dann habilitiert, nicht so weit weg von hier, an der RTWH Aachen. Dann hat sie ihn auf eine erste akademische Position nach Stockholm verschlagen, und aus Stockholm ist er dann zu uns gekommen. Und ja, wir werden heute über ein Blind Date hören, Blind Date Sustainability meets Inorganic Materials. Wir freuen uns auf deinen Vortrag.
Danke, danke. Lieber Herr Dekan, lieber Fabian, vielen Dank für die Einführung, für die Einladung. Ich werde für den Vortrag ins Englische wechseln, weil wir auch viele nicht deutschsprachige Zuhörer haben. Alright, with this, I mean, you can see already here in the slide, we have to see if we have a match between both parties, sustainability and materials. And I would say we just give it a try and we see what comes out. Now, before I start the talk, I would like to show you maybe the people behind the science who actually allow me to speak here today, because they're making the work in the lab. I would like to thank the scientific co-workers, the senior researchers, Björn, Eduard, Bruno, and the students, Lucy, Andreas, Vanessa, Maria, who's at Linz right now, Madeline, Jan Bing, and Nele. I also wish to work of previous co-workers who have either stayed in academia or have gone to industry during the last years. So these people have done the scientific work in the lab, which allow me to present here today. And coming to the topic, I think we have to look at some definitions at the beginning to see where we maybe have this blind date. Now, sustainability itself, there's a definition by the US Environmental Protection Agency, and it's the creation and maintaining the conditions under which humans and nature can exist in productive harmony to support present and future generations. And in 1998, John, Warner, and Paul Anastas coined the term green chemistry. In short, it's the design of chemical products and processes that reduce or eliminate the generation of hazardous substances. With this in mind, we can see, we take our both players on a blind date. We would have here sustainability, for example, and here's materials. They have met at this table and they see if they have something in common, actually. You may think that a blind date nowadays would be you have two personalities maybe chatting over their iPhones together and seeing what can come out of this. Now, which areas can we address in such a constellation right here. And I believe it makes sense to take a look at the Sustainable Development Goals, 17 SDGs. Which areas can inorganic materials influence? And I have marked here in black, that's a chemist. And in my opinion, we can influence 16 out of 17 of these. This would be tough, but actually in each of this, chemistry plays a role. If you think about food production, without the Haber-Bosch process, basically impossible. Or if you think about climate action, all of you have heard about CO2 and the CO2 levels rising in the media. Here I have for you a curve of the CO2 concentration as a function of time. So you see here, this is the point where industrialization kicks in and the numbers go up quite high, and it contributes to global warming. And how can we address this with materials? Can we maybe reduce it? Where are the problems? First of all, if you listen about 400 ppm, it sounds like a big number, but how much is actually 400 ppm from a chemist's perspective? I have here for you the atmosphere in black dots, and the contribution of CO2, it's marked in red. Can you see it? Yeah. So you see we have here an equivalent problem. We have a contribution to global warming, but it's tough to reduce it because it's such a diluted solution. So in my opinion, you rather have to go to the direct emission source of the CO2 to get a higher concentration, to get a process which is more realistic. But we can, with materials and solar energy conversion, run in principle our economy like this. We can reduce the CO2 with renewables to, let's say, formic acid, which is also a hydrogen carrier. And this could be used that you then free the hydrogen and you run the economy on it and you get back to the water. This requires, first of all, that you have materials which kind of mimic nature's approach to do these reactions. And how does nature do it? Nature works with interfaces on a very small scale, and that's the nanoscale. So if we want to go to the scale of nature, we have to make materials with interfaces at the nanoscale in that case. Now, there's also another problem, and I call it the carbon tragedy. Many numbers, but just take a look at this equation here. This is basically on thermodynamic data. How much energy do you need to reduce CO2? Here we have 6 CO2 molecules, and you can see here the result around 3000 kilojoules per mole. So what I would like to say with this is, if I have an infinite amount of energy, I can do everything. If not, I have to be maybe more specific. So it's not so easy to go to solar fuels. But let's make the test if materials and sustainability can be a match, and we think about CO2 reduction. We can use the energy of the sun, solar energy, so we need semiconductors which can absorb the light coming in. And we need a chemist who can analyze materials on the nanoscale. So what you see here is a polymeric carbon nitride. It's a semiconductor which can absorb visible light with a band gap of 2.7 electron volts. But we also need interfaces with a catalyst. So these black dots here, these are small, tiny platinum particles. And if you have this interface, you can run an integrated photocatalytic system to reduce CO2 directly to form it, for example. We can add color to these TEM images by using spectroscopy, nanoscale spectroscopy. And you can see here that we can extract the chemical information to get platinum on these materials. Does the interface work? What we get actually is formic acid with 150 millimoles per hour per gram of catalyst, but we get a very high selectivity, over 95% for the competing reactions like carbon monoxide formation and water. So we as chemists, we can design materials to get the higher performance. We can make such light absorbers, make the interfaces with platinum. That's how an embedded system can work. So this shows you, we go to a very tiny scale and we try to resolve the complex material on the precision like a homogeneous catalyst. And this we can do with spectroscopy actually. If you take NMR spectroscopy, each atom in this polymeric nitride you can actually identify. So you get a complex heterogeneous material with a resolution of a homogeneous catalyst. And this is an embedded system, so we can make one material to get formic acid. But we can also decouple the system to decouple light absorption from the catalysis. So you would take a photovoltaic device, solar panels, provide the voltage by light absorption to an electrolyzer, and then we can maybe make CO2 reduction. And if we swap the material now from platinum to nickel on carbon, we can get actually a very high efficiency for carbon monoxide production, over 93%. How do we do it? It's the question of the design and the synthesis. In this case, we take glycine as a precursor for carbon, so you have a functional group of nitrogen. Then you add zinc to it as a precursor and nickel salt. Then you can derive such porous structures. How do we do it? We start first with a simple solution. We add it together and we make a pre-oxidation step under air. And then we increase the temperature under argon to 900 centigrades, and the zinc leaves our matrix, and we are left with a mesoporous material with a high surface area. And then we can make, hopefully, this high conversion to CO. This is like a C1 basic chemical. Now, how does it look like? Again, we need spectroscopy for this and TEM. We see here a single nickel nanoparticle, and here you can see the matrix of the carbon doped with nitrogen, or rather substituted with nitrogen. And you see here you have the particles. So a nice catalyst. What about the performance in terms of currents? And don't be shocked, many graphics, I will lead you through it. It's actually quite simple. We are measuring here the current density, so how much current do we get out from a specific geometric area as a function of the potential. And we just take a look at this red curve in here. This is the catalyst. So if you start the screen from the right side to the negative, you get a current. And then the current can be used to reduce CO2. And you can take then a current point, a potential point, and collect the chronoamperometry. So you collect the current density as a function of time. And what do we see here? We have at this potential, against the hydrogen electrode, Faraday efficiency, which is like the selectivity of CO2 reduction to carbon monoxide, and it's actually quite high. But the selectivity has to be coupled also to the performance of the current, and which you can see here, it's like above 20 milliamps per centimeters, and this positions this catalyst right now among the best performing ones. But the key step is to get the design from the chemical perspective and to make the material which shows a high activity and is also stable for a longer period of time, like 10 hours. It doesn't help you if the catalyst deactivates after 10 minutes, right? So we have two possibilities. We can make an integrated photosystem. We can also decouple it, actually, in this case. Now, how does nature recycle, actually, CO2? Nature also emits CO2, but it has made a recycling mechanism. And that's the biggest advantage of biomass. So it's a bit coming back to the first question with the low concentration. The advantage of biomass, it's continuously being reproduced all the time. Whereas when you make polymers out of crude oil, you first break the crude oil down to smaller molecules, and then you rebuild it up with catalysis. But why don't we just go the full way from biomass to the polymer? Which biomass does nature do? We have cellulose, hemicellulose, and a so-called lignin. And this is around 30% of all non-fossil carbon on this planet. We extract 50 million tons per year, but we only utilize 2% of it. The rest is just being burned, and that's why people say you can do everything with lignin except money. But I don't believe it so much, actually, because if you could cut here these chemical bonds very selectively, you could get to a monophenolic feedstock, which you could use then to make, for example, polymers or other products. But the problem is, how do you depolymerize this? And this is where materials come into play and address directly a sustainability aspect. The basic question is, you have this complex molecule, and we have to find a way, or the hamster in this case, as a catalyst to break the bonds in a specific site. First problem is the solubility. But you can actually transfer your knowledge from CO2 electrocatalysis directly to lignin depolymerization. So the idea is you generate in water the hydrogen, and you use it to cleave the CO bonds, for example. So we apply on a copper electrode, which is a very bad catalyst for water reduction, but a very good catalyst for CO2 reduction. So you have to find this balance between both reactions in solution, and we take this as an additive to dissolve the lignin, and then in theory it looks like this. You have your catalyst, green electrons, and in a spectacular way you break the chains of lignin. But as we know in reality, if you work in the lab, most likely you follow here a slight color change, then you have to make the analysis, isn't it? So what we see here, the color change after 20 hours, but what's inside? And you basically take the complex structure, you put the copper catalyst, you add the power cord, and then you can analyze the different monomers which come out, or dimers, and you see specific molecules which you just get with the reductive approach. You can also oxidize lignin, but then you mainly get acids, because it generates oxygen. The reductive depolymerization, this is the first work, and I think it came in a difference of 1 week with this published paper by the Anastas group. So sometimes you think you are the only one working on this. It's not always the case. But in principle, we can depolymerize this feedstock using renewable energy. And you can also follow in the proton NMR the reaction, how it proceeds, so you can see after a specific time that you increase the amounts of the monoaromatics in there. When we published this on this copper catalyst, I thought this is a very comparable situation to CO2 reduction. So now it's enough just to take the catalysts and just screen them to get a higher selectivity for the aromatics. This was the main idea. So if you have been successful with copper, then maybe we can find a material similar. And then we thought about carbon. Okay, so can we use carbon as a catalyst in this sustainable aspect? And what we got was the same electrolyte in water, but we got as well a color change. So we applied different constant currents and we analyzed the outcome of a reaction. And we were quite surprised because we expected aromatics, but to be honest, we didn't see them at all. Instead of getting aromatics, we made a de-aromatization, which is not bad. But it's quite surprising because you get from this depolymerization mainly these four main products. So usually when you start the reactions to the control, you make it for 20 hours, you see main peaks from levulinic acid and the hydroxyvaleric acid. And if you magnify this area in here, you see that you have a complete de-aromatization. So this shows you how materials design can give you another outcome, and it's always easily to predict it, but the outcome can be quite rewarding. So after having this, also with the copper catalyst, we were approached by our industrial partners to think about a biorefinery, if we can transfer the materials concept to biorefineries. Just one thing, I forgot the slide here. We could make sure that we have also the products in the applied, the advanced analysis LCES IMS with the group of Niels Schepp in that case, because we see with the polymerization product the same standard which we have obtained in here. Okay, so coming to the biorefinery, what's this? I'm a solid state chemist, so I had to do some reading when they approached me. But in particular, when you have a forest, you can get the wood. And then you have a pulping process, you get the cellulose fibers for your t-shirts, for example, and you are left with several side streams. And one of them is one containing these acids like gluconic acid. And it's a big question how you can valorize it. So the question is, how can we reduce it to like sugars, the glucose? So I thought this is straightforward. I just take the same catalyst as before. The chemistry should be directly transferable. Then Maria tried it and it was an absolute failure actually. So we were surprised. The frustration was a bit there, but she looked further on it and she could get a gold-coated silver catalyst, and this was actually quite successful in valorizing this feedstock. So you can see as a function of time against -1 volt that you are increasing the glucose concentration. You need a tandem cell, which is a membrane in here. Without the membrane, you make a decarboxylation of your product. But in theory, you use here a working electrode out of gold. It's the same game, green electrodes, and you make the reduction. And then she also tried the silver. So she made a CV, and we have different potential points. Then you can see what is the outcome. The glucose production is their maximum, and she basically found it at -1.5 volt. Why is this the case? Because if you go to more cathodic potentials, then you increase the hydrogen production from water. But this shows you that you can actually expand from solid state chemistry into other fields you would never have thought about before. If you ask me about the future and the catalyst design, I believe we have to maybe get a bit away from this rational design and maybe think more about in operando measurements. I will show you some data which are not yet published. This is a catalyst which contains carbon and small particles. The question is, how stable is the catalyst during operation conditions? How do we analyze this? We can make a working electrode for the depolymerization of biomass, and you can collect at this potential, for example, a value, the current, to see if something is happening. But how do we follow the structural changes during the operation? You have to go to in advanced XAS experiments, which we did at the Delta together with Dirk Lützenkirchen-Hecht. The first point is you have to get a cell. This is a cell made by a PhD student, Andreas Trichel. Here we have fluorescence detector. Here's the cell. This carbon tape, this is the catalyst. And it's connected with an alumina foil, connected to the potentiostat. You have here the reference electrode, silver chloride, and here you have a counter electrode. And then if a cell is tightly sealed, you can make the measurements. If not, you have a leakage and you run into problems. So this is the magnification. What's required is actually teamwork to do this. Here you see a picture. This is Bruno, Andy, Lucy, and this is me smiling because finally I left the office and did some real work in the lab with experiments. The measuring unit is behind these walls. So here we have the instrument. So one person is to control the potentiostat, the other person is starting the measurement. So here you can see our cell where you shoot in the radiation and you collect it in here. And then you can acquire different data sets and see if you have some structural changes depending on the potential which you apply. And in my opinion, this is like the best way to identify catalysts with the highly reactive intermediate states which we then can stabilize. Okay, so coming to the title, materials, what we have seen now are the electronic effects of materials to influence sustainable topics like CO2 reduction. But we also can work with interfaces, as nature does. And I would switch a bit the gears to an oxidation reaction, and it's the oxidation of carbon monoxide to CO2 actually. Still a very interesting reaction, and I want to show you how we can control interfaces to control the reaction outcome. We make a room temperature CO oxidation. We use two catalyst systems. Both have gold particles deposited on different supports. Here you have megamite, iron oxide, and titania. Almost the same surface area. You have no single atom catalyst. You have isolated particles. And now, is there any difference if you make the oxidation at room temperature? So does the interface play here a role? So we tested this in a flow reactor, and it was quite surprising. This is a curve. It shows you the rate of CO2 production as a function of the time. At this point, we kick in the CO. So it's CO on with water together. It's a catalyst gold and titanium. So no CO2 is being formed. If you add oxygen, the CO2 kicks in. It arrives. Now, if you do the same game with the iron oxide, we throw in the CO in the water. What's this? We have an increase of CO2, but we have no oxygen. If you insert the oxygen, you have an even higher activity. So what's happening here? To identify this, you need labeling experiments. So we labeled here the water with 18 oxygen, and then we read the experiments. And just take a look at this green curve. It's the rate of CO2 production, and you can see it has 18 oxygen and 16 oxygen actually. So it shows you that the water is playing here the source of the oxygen. So from mechanism-wise, it's like a so-called water-promoted mass van Cleveleven mechanism. Simply speaking, the support surface is not innocent. It takes part into the reaction because you have here the gold, the iron oxide. You have the adsorption of CO. When the water kicks in, it gets adsorbed, it splits into OH and H. And then you have the spillover over the interface, you generate the CO2, and you are left with a vacancy behind. And this is a preferential adsorption site for oxygen. So we have actually two tools in hand, the electronic structure, the geometry, together coupled, and also the interfaces. So this brings me back to the question, how can we assign and target sustainable goals with materials? So how does nature make its materials? We do it in the industry. Nature makes an air economy. Nature makes its products by the air directly. So can we make also an air economy? And this is like a basic chemical which we are all using. And the market is still increasing. It's supposed to increase to 5.2 billion US dollars. How do we do it today? We take oxygen and we enter quinone as a catalyst. And after the peroxide production, we basically have to recycle the catalyst with hydrogen to make it active again. Is it sustainable? The question is, where is the hydrogen coming from? So can you maybe do this experiment directly as nature in air? It's also a bit tricky. We first tried, again, this polymeric carbon nitride catalyst. These are many spectra. I just show you my favorite peak. It's this one. It's the graphitic nitrogen, and we collected this without any isotope labeling. The thing is, the abundance of nitrogen 15, it's 0.4%. So usually you have to do labeling, but we found out if you take a very, very big rotor and you could insert 0.7 grams of the material, you can get such a nice spectra after 4 hours. And this gives you, again, a picture like a homogeneous catalyst for this complex material. We can make, with this material, tertiary alcohols, like a hydroxylation reaction, and then we targeted the peroxide production. And this actually works nicely. We get, using solar energy, 2 millimoles per hour. This was the best catalyst 3 years back. Now it has been beaten. How does it work? We need first of all the catalyst, the illumination, and ethanol as a source of hydrogen. So we reduce oxygen to peroxide, we make the oxidation to the aldehyde, but we still need from somewhere the ethanol. And the second problem is the metal salt concentration. If you have metal salts in your solution, your catalyst gets just killed. But as you see, the performance here is quite nice, but we have still the 2 constraints in here. But maybe we are already at the end. So materials think about performance, they propose to sustainability, because materials think that performance is everything, but what does sustainability answer in that case? What about operating in circular concepts? How do we do our materials today? Now you may think that we may be already working in a circular economy because we have learned how to synthesize all types of materials, but are we really embedded in these circular concepts? Maybe we are already. Maybe we are like a hamster here making our materials. At some point we are asking, are we there soon in the circular economy? But maybe we have to look at materials from a different perspective in the lab. I think more how nature includes the recycling mechanism in here. If you ask me, I think we have to collaborate with nature. I would like to have a company which I call Ligninorg, a combination of biomass, lignin, and inorganic chemistry, because nature has given us already its materials. Maybe we can functionalize them further to get a higher performance and also outperform pure inorganic materials. We proposed this in 2020, and I'm going to show you what we got finally. So we made in the same year the Silofort concept. So we grew hydrothermally at high pH on cellulose small semiconductor nanosheets of the bismuth oxygen bromide system. They agglomerate on fibers of cellulose, and we can scale this up to like this size to get a membrane. You can see the SEM image. This is cellulose coated with the particles, and it can do 2 tricks at one time. If you have wastewater with organic pollutants, you can decompose them by photocatalysis. Here's rhodamin B. Because you have a semiconductor, so you have the holes, and they can basically oxidize the organic matter. And you also have the functional units of cellulose, and you can use them for adsorption of metal ions in the water. And then we thought, can we do the same for the air economy to get basic chemicals? So as you see, seawater has 97% of metal ions, with seawater is salt water. So can you make the peroxide production directly from seawater, was our question. A reaction seemed impossible, but we gave it a try. The main idea was we could go collect the seawater, put the catalyst in there, put it to the sun, and then collect the peroxide. Very naive, but we tried it. Here's the structure of the catalyst. We grew on lignin, specific type of lignin, which is stable at high pH. We grew the bismuth oxygen bromide system, the 111, and then we tested it with simulated seawater, 0.6 sodium chloride. This is the production of peroxide, this is the time. The blue curve, it's the inorganic catalyst, and after 1 hour, as expected, it dies. Then we grew the nanosheets on cellulose and on graphene. After 1 hour, they were also dead. Then we tried it on lignin, and look at this guy. He continues to make peroxide all the time, in simulated seawater and also in real seawater here. So after 1 hour, we start the illumination and we generate here the peroxide. We first thought it's coming from the lignin, the oxygen, but we also made labeling experiments with 18 oxygen, and we could collect them to make sure that we have the peroxide from the gas coming in. So what I would like to say here is it pays off making green chemistry, because you can outperform pure inorganic materials. Why does it work? We tried first of all different types of metal ions, salts, a thing we usually do when the reviewer asks for it. The structural stability is given here. This is the bismuth oxygen bromide before the reaction and after the reaction on the lignin. So you have the same reflection peaks, so we can say that they are stable. You can see here the structure of the lignin with these agglomerated nanosheets. And what's happening in here, we found that we have a shift in the band edges actually. If you have the lignin with the photocatalyst, you have a higher conduction band edge than for the others. So my thought is that by modulation of the electronic structure in this case, which we see here from the Schottky measurement, you can most likely influence the reaction parameters in here. So you can see we can address with materials sustainable goals by working hand in hand with nature. And there are also other aspects of materials, not only catalysis. I would like to show you how green compounds can substitute today's technologies. And that's why we also need nanoscale spectroscopy. If you think about engines, you need lubrication usually for the metal elements. What you usually do, you have a reference oil, you have some additives. And maybe you know this compound, ZDDP, ever heard of? It's an additive. This organometallic compound decomposes in operando to a polymeric film on the surface, and then in the end at the end of the life cycle you have some carbon soot particles, and people thought you have this polymer there, it's safe. But if you go for nanoscale spectroscopy, yields combination with EDX, you see that actually in this carbon soot particles you have such zinc oxide particles doped with phosphorus and sulfur. The other thing is, where is the ZDDP being produced? That's a big problem since 2 years, you can say, for some reasons. So our industrial partner approached us if we can find a substitute for this. So we thought, let's give it a try, let's work hand in hand with nature again. And we thought to use lignin. The problem is the stabilization. We found you can stabilize the lignin also with organic chemistry by making an esterification reaction. You make it more hydrophobic, and then you can precipitate it out as a nanoparticle in solution. And this expands your window of application. Here you have pure lignin at pH 7, at pH 12 it dissolves, so it's not a template anymore. And at pH 2 it's a chunk, it agglomerates. But if you make this reaction, you can expand the stability window for high pH, and you can then also make the hydrothermal growth of materials. We tried the MOS2. You all use it actually for your bicycles. It's like a spray where you make a lubrication for your chain. Now we try to grow it on the lignin. Here you can see the control. These are pure MOS2 nanosheets. You can see here the 2D structure, and then we grew it on the lignin inside. And here I really like this interface image. This is the lignin nanoparticle interface with the 2D material. Chemically speaking, this is here your interface. But this nice image is not enough. You also have to convince with the performance. With the Austrian Excellent Center for Tribology, we made the tests. We first tested the coefficient of friction. This is the reference oil. Then we add our material and we have this value, and it's like the same like ZDDP. But you have to also make the scratch test. So you take basically one metal element, you add the lubricant, and then you go 10,000th time and you see how much wear you have of the surface, which you can visualize then. So if you have just the reference oil, you have 12 micrometers to the power of 3. Adding our substitute, we decrease by 70%. So again, I think this combination is quite nice if you use inorganic chemistry and biotemplates. You may think, why just not use MOS2? This is correct, but industry wants to decrease the amount of MOS2, so there's still a driving force that you just minimize it in that case. So as such, I'm advancing in my talk. I have maybe one more aspect for our blind date. We have talked about solar energy conversion, catalysis, energy storage, not so much. I will not go into detail here. I will talk about recycling of batteries actually. Maybe I would ask first, do you think that recycling of batteries is today sustainable? Who is for yes, who's for no? Yes? Nobody raises his hand? Fewer? I have here the most advanced recycling process. For details, I would refer to this paper where we have the companies more specified. But if you use recycling, if you do recycling of batteries, you basically have many problems. One problem is the electrolyte, where you generate in situ HF. And people are speaking about battery passports, so you can identify and separate the battery chemistries from iron phosphate and NMC cathodes, but in reality, you get like a big chunk of thousands of tons of different batteries in a big batch. What do you do with it? How do you separate these batteries? The other problem is you generate you have lots of wastewater. It's not a circular process. You have solid waste, use solvent, complexing agents, and you also generate in situ during the process toxic chemicals. So it's really a problem how to do this. So far, recycling was sustainable in a circular way, that people were just shifting their waste aside to the next company who thought who can recycle it. But I believe that we can achieve this by combining green chemistry metrics. What do we need? We need the cobalt, we need the lithium, and how do we get these materials today, these raw elements? Cobalt, 75% from the Congo, under not really ethical working conditions. I would say the critical raw elements are already here in Europe. We just have to find a way how to recover them in a sustainable way using chemistry. Because this is the keyword, secondary mining. We have to find a process which works in a circular concept, and my advice is to first not use chemistry too much in the beginning, because then you make the production of toxic chemicals because you don't know the chemistry of the battery. You have to be efficient in terms of energy, CO2 emissions, and also have a potential for circularity, and you also need this lifetime monitoring or online monitoring. Now, how can we do it? We entered this with our bio-inorganic composites. We could make composites with silica and lignin. I call it solid state filtration. So the idea is you take a battery, you leach out the critical raw elements in solution, you throw in this powder, and then you adsorb on the surface the metal ions, and you recover cobalt, nickel, and so on. Then you can take this adsorbed powders to another solution, change their pH, and recover them at room temperature. It works quite nicely for these composites. Here's the uptake of cobalt which we can get in these, from these batteries, because you have here the functional groups where the metal ions can adsorb. For separating cobalt and nickel, there are more tricks. I would maybe refer to this paper here. But cobalt and nickel is not everything in a battery. You also have a current collector, copper. You also have manganese from the NMC cathodes, which are used in cars, for instance. How do we get these out? So we took real batteries. And this is my first advice: use a real waste of battery, because these simulated solutions make some problems. We leach the critical raw elements, and then we have a solution with copper, nickel, cobalt, manganese, and then we applied electrochemistry at room temperature. We used a steel electrode and a carbon electrode, and we applied a potential of -0.5 volts. And what happens here, we drag the copper to the left side in the reduction step, and the manganese to the right side. So what do we have here? On the cathode side, metallic copper with some copper oxide, and we have manganese oxide in amorphous powder on the anode side. If you then think about the solution, this is the ICP analysis. Copper is basically gone from the solution, manganese as well. So what's happening here is that you can compare kind of playing poker on a round table. When we come from the outside with two electrodes, copper goes to the left, manganese to the right side, and these guys continue playing because they see no potential in here. And then you can separate them in the next step, and you can recover the whole solution, basically. So coming to the main question, can materials be sustainable? Inorganic materials. They could be sustainable, I would say, but stability under operating conditions. CO2 reduction. You need a longer process of time where you can analyze the catalyst. Because if you have some ppm amounts of iron in the solution, they will get adsorbed on the surface and you have a catalyst for water reduction. So stability is a problem. We need a potential for recovery of the materials with 100% or almost 100% function, because you have to work in a circular pathway. And we need the scale up to go from invention to innovation, so commercially attractive materials, low energy, low pollution, and this potential for circularity, like you've seen with the batteries. And for catalysis, I believe very much in operando studies to identify the most active catalytic sites, and then in the next step you can think how you stabilize them chemically. Now, what about our couple? I think we have here a power couple who's working in the lab. Sustainability on the left and materials on the right side. And I think this is a good match for the future, and it's a required match for the future. I would like to thank again my group for their hard work. I would like to thank their collaboration partners. I namely named the professors for space reasons. I would like to thank the industrial partners and the funding agencies. And also, since this is an inaugural lecture, I would like to thank my academic supervisors, Reinhard Nesper from ETH Zurich, who was my PhD advisor, Professor Pei-Long Yang from UC Berkeley when I was a postdoc, and Professor Richard Gonskowski, who was my mentor at the RWTH Aachen University from 2014 until 2019. And if I would have to make an outlook for the future in terms of our role as professors. I think we need a change in technology to more sustainable solutions. And I think there are two pathways to achieve this. One way is that you block the streets, destroy art and paintings, and you just draw attention to it. The other way is, I think you have to go and research on new technologies. And this involves curiosity, creativity, and collaboration. And it's the most challenging part here, but I think all of us have to make a decision here for the future. And it's our role as professors to work with young students and work on these technologies. I would like to thank you for your attention and for the invitation here, Fabian, and thank you very much.